Okay, example number 3 here has us analyzing a reciprocal function and using a very common example out of electricity. So if you're in physics and you're studying electricity and currents, you're going to deal with this reciprocal function all the time, which is that I equals V over R. Okay, this stands for the current is what you get when you factor in two things, your voltage and your resistance. Okay, in other words, the current, or so like if I want to draw this out, let's say I've got like a little battery here, got a plus side, a minus side. We have a current coming out, and it goes through a wire. Okay, so we just connect a wire from the front to the end of the battery. So now the way that batteries work is that you've got a certain amount of charged substances that are separated. So over here is a bunch of positively charged stuff. Over here is a bunch of negatively charged stuff. Oops. And the electrons that come out of this get pushed away from one end, um, and they end up getting attracted to the other end. So the way that this is sometimes electricity is a little confusing because the way that the pluses and minuses were decided on originally don't lie up to our future understanding of how things work. So if you have any chemistry knowledge here and you understand that typically electrons flow through metals, protons don't. So really, it would have been much better if batteries were labeled this way because really it's the electrons, it's the little negative charges that are going to be getting pushed away from each other and going to get attracted to this positive end. Unfortunately, that's not the way that they labeled them originally, and it leads to all sorts of confusion for physics students. Um, Regardless, talking about this statement here, what they're talking about is the current. So that's like the flow of electricity. Do you have like a lot? Do you have a big flow of electricity, a lot of electrons moving per second, or do you have a smaller flow of electricity? Well, that depends on two things. It depends on the voltage. Voltage is kind of like the pushing force. So, for example, if we had a battery, we kind of make some rough sketch. If we have a battery and there's some separation here between the negative and the positive, and there are four electrons versus a battery with three electrons. Well, what hopefully you know is that like charges repel. So if you have a bunch of stuff that all has negative charges, these electrons here, they don't want to stay together. But four of them want to stay together even less than three of them do. So the one with the greater voltage would be this guy. This one has more electrons that want to push against each other, and they are going to shoot out their electrons with a greater force because there's more in there. You can think of current, voltage, and resistance. There's a very easy metaphor to like analogy to like having a hose. So if you have a hose, you have a certain current of water. The voltage is like the pressure, how much water is down the hose pushing on itself. So if there's just a little trickle, that might be because there's not a whole lot of pressure pushing on the water. Now, the final thing is resistance. So if you're talking about a hose, you might be talking about, well, what about a hose that's full of rocks and it's hard for the water to get through? Or if you think about a big hose versus a really narrow hose, those might allow the water to travel through differently. Same thing would apply to wires. So if you have like a big, thick wire, it may be different. It's going to give it a different physical environment to move through. So it may have an easier or harder time depending on the size of the wire or the material of the wire. Copper versus tin. There's a reason why we use copper wires. It has a very low resistance to electricity passing through it. The electrons don't get jumbled up in there. So regardless, the example we're getting here is about current, voltage, and resistance. And it's just saying that how much electricity flows through a circuit depends on two things: how hard that electricity is getting pushed through the circuit and how much that electricity is getting slowed down on its way through the circuit. Okay, so if you know those two things, how hard it's being pushed and how much resistance there is, then you should be able to tell me something about the current. And if you know any other two things, for example, if you know the current and the voltage, you should be able to tell me what kind of resistance we're experiencing. If you know the resistance and the current, you should be able to tell me what kind of voltage is pushing that current through. Okay, it's just kind of simple three-part scenario where if you know two of them, you know the last. So in this case, the current, well, typically in many situations, you'll have a constant voltage. So for example, here we say a voltage of 110 volts for a curling iron. So we have 110, we have a stable 110 volt current. So that's just like based off the, if you want to say, the amount of batteries or the size of the battery or how the curling iron set up, it produces this much pushing force on the electrons going through it. And then you've got some sort of variable resistance. So this is where on the bottom of our equation, we've got, we're going to have some linear variable. And they're saying the resistance is variable. So that could have to do with like maybe how you change the settings. So if you imagine on like a hot curling iron, there could be like low, medium, and high temperature settings. Well, that temperature is going to be based off how much current is going through. If the voltage is constant, then there's going to be something to do internally in this device that's allowing us to change the resistance. They're probably not swapping out different types of wires. Maybe they are changing the length that of the wire that the electricity is going through. Maybe you're changing from like one diameter to another. Whatever it is, we're imagining that this curling iron has the ability to change its resistance in the circuit. Okay, so as that resistance increases, as this gets larger and larger, that current will drop down. And in this case, it'll drop down approaching zero, right? Because we don't have any like +5 on the end. It's not dropping down to some value out here. It's just in the long run, a function that is a reciprocal function. As R gets greater and greater, the current, which we call I in electronics, the current drops down to zero. Um, yeah, that's all there is to it. So we're just looking at a real world application of one of these reciprocal functions. Look on here, make sure there's nothing else that we want to talk about. Because V is 110, the current would be 110 over R. We have a vertical asymptote at R equals 0 and a horizontal asymptote at I equals 0. Okay, sounds fine to me. Let's take a look at the next page real quick. Okay, so they're saying you can make a table and plot this. So if it was going to be that 110 divided by R, you'd get a bunch of values for your current. You'd be able to take those values, put them on your graph, and connect your points. You could go through with your equation and try to solve for x and y intercepts. However, on this one, I don't think we ever touched the x or y axis, so there wouldn't be any x or y intercepts. And we would just have general end behavior to describe. As r approaches negative infinity or as r approaches infinity, in either direction on our variable axis, as we go out to the right or to the left, we approach a voltage of 0. I don't think that should say V. That should say I up there. They mislabeled that. It should approach a current of 0. Okay, and that's all there is to it. You could read through this second example. This is about like there's a set cost on a cabin, and the more people who are sharing it, the less they each have to pay. That'd be a reasonable reciprocal kind of function. As you increase the number of friends, each person pays less, that kind of stuff. So we're just dealing with kind of simple fractional functions where the denominator is the variable. Okay, and I don't think there's anything more to talk about on that example. We'll move on to, in the next video, learning about transforming reciprocal functions, and then we'll go through a few examples of those transformations. All right, I will talk to you in the next video.